Flood is a widespread and conductive natural event, often leading a significant economic, environmental, and social sequence. This project allows students to apply their hydrology knowledge and technical skills to design a flood mitigation pond using SAC-RAS software for flood routing and hydrological modeling. This encourages creativity, teamwork, and collaboration while also emphasizing practical solutions. Students will gain experience in project planning, report writing, and using available data, bringing gap between theory and real-world water resource management.
Objective we get from the project is to analyze the flood patterns and hydrological behavior of the study area using relevant data. Second, to propose a flood mitigation pond with an appropriate shape, size and concept based on the group's creativity and the site's needs. Last, to utilize the Hydrologi model to simulate and evaluate the effectiveness of the proposed pond and reducing flood occurrence.
Okay, next we go to result. High flood deep zone located near river bank and flat topography to natural ponding area. Low velocity flow area that the velocity is below 1.0 ms, ideal for detention, sediment deposition, and stability. Reason for site stability, natural water collection is exactly deep indentation indicate natural potential for ponding. Reduce erosion risk is low velocity flow ensure pond investment remain structurally sound. Okay, we go to embossed terrain capability. Wide footprint area allow for large volume pond construction. Okay, next is of access, proximity to existing route, infrastructure support, maintenance, and monitoring. For flow depth analysis, make flow depth higher 3.5 meters. 2 versus near low-lying zone and riverbed. This area naturally retain water to ideal for flood mitigation ponds. For velocity profile inside, high velocity up to 2.5 ms in narrow channels to erosion risk. For low velocity, below 1.0 ms in broad floodplain to suitable and stable for pond placement. And for cross-section profile, well-shaped river geometry with wide cross-section, step bank and natural containment minimums major earthwork. Discussion effective of headrise simulation. The headrise model provides reliable insight into the flood behavior within the study area. By analyzing deep, velocity, and cross-section profile, the simulation effectively identifies vulnerable and stable zones for mitigation planning. For interpretation of key results, deep analysis confirmed that low-lying area near river been experienced severe inundation higher 3.5 m, making them ideal for flood pond placement. Velocity analysis discusses area of high erosion risk and low flow zone suitable for stable pond construction. The cross-section at station 2443 demonstrates that the terrain naturally supports flow storage, minimizing construction efforts. For model limitation and exception, simulation based on single flood event. Results may vary in different return periods. The model did not account for land use change or infiltration, which could affect flood spread and storage. For practical implication, despite its limitation, the model proved that hydraulic simulation is a powerful tool in early-stage flood mitigation planning. The insight directly informed the design and setting of a multifunctional pond that can reduce flood speed and improve downstream release.
For the implication of this project, our flood mitigation pond design has shown that it can effectively reduce flood risks by managing peak runoff and storing excess rainwater. In addition of its main function, this pond can also offer environmental and communities benefits such as improving local biodiversity and supporting sustainable water management. This demonstrates how engineering solutions can contribute to safer and more resilient urban areas.
Conclusion: effectiveness of headrest model. The headrest model successfully simulates flood behavior for the Salad River Strait. It provides reliable terrain and flow data, guiding the design of a multifunctional flood mitigation pond for flood risk identification. The 5 September 2008 simulation highlighted critical zone deep higher 3.5 meter in low-lying meanders, low velocities ideal for water retention. These findings confirm the natural sustainability of certain area for pond construction. Conclusion: effectiveness of headrest model. The headrest model successfully simulates flood behavior for the Salad River Strait. It provides reliable terrain and flow data, guiding the design of a multifunctional flood mitigation pond for flood risk identification. The 5 September 2008 simulation highlighted critical zone deep higher 3.5 meter in low-lying meanders, low velocities ideal for water retention. These findings confirm the natural sustainability of certain area for pond construction. For future recommendation, modeling and data improvement, conduct simulation for multiple return period. Integrate real-time rainfall and stream flow data to improve model accuracy and support early warning system. For environmental and structural adjustment, evaluate pond potential for sediment and pollutant removal to support multifunctional use. Integrate pond into existing urban drainage system for better flood control. Ensure embankment stability, erosion control, and long-term maintenance planning. For community and climate consideration, engage the community in maintenance and flood awareness campaigns. Design pond with climate adaptability. 2. Preparedness for increased rainfall intensity and future scenario.